So hopefully everybody's not in a food coma here. I want to do a quick survey because I know there's a containers room going on, and we're kind of talking about containers here in the distributed systems track, and we'll get to why. How many people here are using containers in some manner? Yes. All right. How about container orchestration? It doesn't necessarily have to be Kubernetes. Okay, a smaller group. Okay. So I'm a cloud developer advocate at Microsoft, where I primarily focus on distributed systems and Kubernetes. So I want to talk about what is Kubernetes, like at its core, what is Kubernetes? And if you ask people, a lot of people might start with things like it's a container orchestration platform. And I mean, what does that mean, really? And then we've got infrastructure as a service platform. And a lot of people mean this because there's a lot of tooling built in as far as self-service infrastructure. But the question I want to pose to everybody is, how many people would consider it a framework or library for building your own distributed systems on top of? We've got like one or two. All right, so hopefully by the end of this talk, I can change your mind. So over the break, I promised myself, the winter break, I promised myself that I would kind of stay away from programming as a hobby. And so instead of that, I watched a TV show about programming. I don't know how many people have seen the show Halt and Catch Fire, but it's really awesome if you haven't seen it. But in the very first episode of the first season, they make a comment. One of the people on the show says, computers aren't the thing. They're the thing that gets us to the thing. And that kind of really resonated with me with the way I had been looking at Kubernetes over the past couple years. So I'd like to borrow that and say that Kubernetes isn't the thing. It's the thing that gets us to the thing. And what I mean by that is it's not that Kubernetes isn't an innovative technology that's helping solve a lot of problems that we have right now. I want people to start looking at it's not the final product. This is the assembly language of distributed systems. We now have a shared way of talking about infrastructure, and the tools we build with it and on top of it are going to be what's really innovative. So in thinking about this, there's kind of two approaches. One is customizing Kubernetes to fit your specific workloads, and this would be in the context of not building your own schedulers and distributed consensus protocols and coordination protocols and things like that, and building it on top of Kubernetes instead of building your own. And then we'll move into kind of building abstractions as layers on top. So first, we need to talk about how Kubernetes works. How many people here are familiar with how the control plane of Kubernetes works? Okay, we've got just a couple. Awesome, you're in the right spot. So we can think about Kubernetes as just a basic reconciliation loop. It's just constantly taking desired state and reconciling the actual state towards that. So we've got a series of Kubernetes objects, and the ones that are listed here aren't necessarily important, nor is it a comprehensive list, but the general idea is that we have this declarative API where we submit these spec files with our desired state. And in this example, the number of replicas and the fact that it's an Nginx image are the only things that matter. We submit this to Kubernetes, it does its thing, and if all works well, we get 2 instances of this running. And all of this is handled by the control plane. So we've got a couple of components that run on all of the worker nodes, and this is all where your pods end up. We've got the kubelet, the kube proxy, and whatever container runtime. And then we have our master nodes with some control plane components there. I have etcd listed here. Typically in a production environment, you would probably run those on their own nodes, but there's only so much you can fit on a slide. So at the heart of Kubernetes is etcd, and a lot of people don't necessarily realize this, but so etcd is a distributed fault-tolerant database. It uses the RAF consensus, distributed consensus protocol that Jeff was mentioning in his talk this morning. And it's essentially a key value store that uses a directory hierarchy where you can watch individual keys or the parent directory for changes, additions, things like that. And it has some primitives in there like distributed locks and leadership election. And most of Kubernetes is actually built on top of this. So the next layer up is we have the API server. Now all of the control plane components communicate with the API server. And basically it's just transforming information from those into the data that's stored in etcd, watching for changes, and notifying the individual components of things that change. So as we walk through these, I want to kind of talk about, in building your own distributed systems and solving unique problems that your use case might have. Let's talk about extension points and how and why you might want to customize it. So the API server itself, we kind of have two ways that we can inject ourselves. One is through API server aggregation. So essentially what this means is you stand up a service and you augment the API server with this service. And we'll talk about some interesting use cases like service catalogs for that. And then we have custom resource definitions. And this is where you think about having a pod spec. You can actually introduce your own types into Kubernetes and have your own controllers that interact with the system based on changes to those. So Open Service Broker is actually a really good example of API server aggregation. So essentially what this allows you to do is expose other services to Kubernetes that aren't necessarily supported. So examples of ones for Azure specifically is we expose Cosmos DB in our MySQL offerings and things like that. And an example of how this works, essentially what happens is the API server communicates with the service catalog. You can list the things that are available. You can provision them. And then binding essentially gets you the credentials to communicate with it. And that's mounted in as a secret into your container. So this is kind of a quick example of provisioning MySQL on Azure. You submit a spec file just like you would for your pod. And you say, I would like a MySQL, and this is kind of the plan that I want to use. And then we can create a binding in order to get the credentials for that into our container. And this offers a lot of power, and with the API server aggregation you can create these things for yourself, your own self-service infrastructure for things that may need to be created, especially when you have multiple teams. Rather than kind of having to do these custom one-offs for people, you can expose just the API for them to spin up their own instances of some internal service. So now let's talk about the controller manager. So the controller manager is kind of the thing that gets kicked off when we have something like a replica set. All it's doing is it's watching the API server for replica sets. And then its only job is to now check the API server for pods that match the labels in that replica set. That's it. And then if the number doesn't match, it creates or deletes them at will. So it's not doing anything to the hosts or anything. It's just managing other resources inside the API server. OK, so inside the controller manager, there's actually a series of reconciliation loops, some that manage the nodes, the replication controller I gave an example of, the endpoints controller, which is what matches services to pods that match those labels, and their readiness probes are succeeding. Then we have a cloud controller manager, which is kind of the thing, works similar to the other controller manager, except that it knows a lot more about your cloud provider's APIs and can kind of do more inspection of the health of nodes and things like that before removing them, setting up routes on load balancers, mounting in volumes for cloud storage that you might have. So the controller kind of pattern, why would you want to create your own? The obvious one is if you are a cloud provider and you want your managed services to be supported. But the main things we want to look at is kind of the decoupling your applications from the resource spec definitions. This gets messy, right? For most of our services, we end up with 5, 10, 20 YAML files to deploy our services. And then if you have to run multiple instances of these things, it gets really kind of gnarly at first. And then even some things that you might have custom stuff built for. So you might want to create self-service infrastructure. And abstracting operational knowledge. And I'll actually walk through the operator pattern, because this one is really interesting. And if you want to create your own controller, there's a link on the slide for kind of a sample controller to base it off of. So KubeLego is an example of a custom controller. So it basically runs in your cluster. It looks for this annotation on your service definition. And then it will look at your ingress, and it will find all of the hosts running in your ingress, and it will go out using Let's Encrypt, fetch certificates for them, and configure Nginx for those certificates. And all of this stuff kind of just works for free. You don't have to do anything custom. So the Prometheus operator is actually one of my favorites. So an example of how the operator works is you can create this new kind called Prometheus, and now you can just request that I would like a Prometheus instance with 2 replicas, and then the operator is watching that, and then it goes out and it creates a stateful set and does all the volume, all the volumes and stuff like that. And it also has operational knowledge as far as upgrading. So I don't have an example here, but you could say the version of Prometheus that you want to run, and it could recognize that it's running an older version, and it could do the upgrades for you. So you're kind of baking in this operational knowledge into the cluster itself. The fact that it creates a stateful set is a side effect. The important thing here is that like the API we expose to the people consuming our self-service infrastructure, they only care about the spec, the desired state. They don't really care how it gets implemented. So the one part that I really love about the Prometheus operator is this other type that gets created called a service monitor. Now, the service monitor, what I essentially do there is I'm just telling it that any pod that matches these labels, I want you to hit it on the HTTP port and scrape Prometheus metrics. And like, think about the power of something like that. I don't have to communicate with operations teams to ask them to reconfigure Prometheus, Prometheus to come scrape my new application. Or when I decide to tear it down to reconfigure Prometheus for me. This is kind of automated behind the scenes. And it's ridiculously powerful. So hopefully this doesn't get me in trouble with my current employer or past employer, but prior to my current role, I worked at Comcast. And a really interesting solution that we came up with was using custom resource definitions to represent video streams. They were essentially replacing this industry-specific hardware called a cap that exists up in these head-end locations, the blue locations, and it multiplexed video together, and then it pushed it out to these devices called apexes, and this used quadrature amplitude modulation to basically modulate the video onto the coax cable. But it had a lot of problems with, how do we schedule these workloads so that they end up as close to the customer as they want. And all of these things we start thinking about, most of us build distributed systems for a living. We start thinking about building our own schedulers and all these things, and it's actually pretty straightforward to just use Kubernetes for this, right? We have host affinity, and pod anti-affinity selectors and all kinds of things that we can use to help hint to the scheduler. So essentially what we ended up doing was creating our own custom resource to represent these streams, and now the video engineers only had to configure desired state. Here's the channels, here's where their inputs come from, here's the ad zone that this needs to actually be deployed to, and then this kind of created a nice separation between them and the system administrators that kept all the infrastructure running. The infrastructure folks only had to focus on ensuring that Kubernetes stayed healthy and the nodes stayed healthy. They didn't have to worry about all of the operational aspects of that. And the video engineers didn't have to have SSH access into all of those, hardware. So when we start looking at custom resource definitions versus API aggregation, there's a lot of similarities. There are some differences. So, CRD, obviously your controller you can implement in whatever language you want. API aggregation, you have to use Go. I personally love Go, so for me it's not a problem, but if you don't love Go as much as I do, maybe that is. CRDs, you don't have to handle multiple API versions, whereas API aggregation you do. There's limited validation right now. They're working on more for custom resource definitions. Obviously, if you do your own API, then you can do whatever validations you want. Sub-resources, you can scale, and you can support status on your custom types. And this is actually really awesome when you think about stuff like this, right? Like, so let's use the video stuff as an example. I can literally do a kubectl kubectl status on a particular video stream and see the metrics for it, right? Because we're just creating it, we're treating it as a type in the system like anything else. So we can scale it, we can report stats. Those are the only things that are supported on CRDs, but on the API aggregation standpoint, you can create new sub-resources so you can exec or attach to these things at will. So now let's talk about the scheduler. The scheduler, right? Like the most complex piece, right? It's actually fairly simple when we look at the interactions. The algorithm itself uses bin packing, and obviously there's some complexity in the way that's implemented. But when we actually look at the role that it plays within Kubernetes itself, it's actually pretty limited. It watches the API server, basically like a long pole, for any pod or job or things like that that does not have a node name assigned to it. And then its only job is to do its thing and decide the node, update the spec, and push it back to the API server. That's it. That's the only role the scheduler plays in all of this. And I think that confuses people sometimes because I think a lot of people want to assume that it's the thing that actually puts stuff on the node. But you can create your own scheduler. And the beauty of this actually is you don't have to replace the default scheduler either. You can actually run them side by side, and you can tell specific pod types and things like that to use a specific scheduler. And this is actually super powerful when we think about designing distributed systems, because maybe the way the scheduling works is not, ideal for our particular use case. So why would you want to write your own scheduler? Anytime you need outside information to make scheduling decisions. Maybe you have things like hardware encryption modules or FPGAs or things like that. And let's say your hardware encryption modules are primed for specific data sets, or you're using secure enclaves or something like that that Kubernetes isn't aware of, and you need to try to use that information. Network-based scheduling. Currently, Kubernetes doesn't support that. Maybe you're doing something like video streaming, and you can easily saturate switches, and you want to use SNMP or something to retrieve metrics from these things and use those to make scheduling decisions. Maybe you have large amounts of data that you need to work with, and you want the scheduler to try to run the workload on nodes that contain the data or as close to it as possible. So kubelet. So kubelet actually is the workhorse. It runs on every single node. And this is the thing that actually calls out to the container runtime and the image repositories, and it mounts volumes and sets environment variables using the downward API and config maps and all that jazz. It provides an API server, which actually the Kubernetes API server calls out to anytime you do something like an exec or attach or logs. And it collects all the metrics that are used by the scheduler and reported to the dashboard. So we can kind of look at this as a basic example. So it's just basically doing a long poll to the API server, and we'll notice this is a pattern with all of the components. And it's looking for things like pods or jobs that have a node name that matches its node name. It's like, oh, okay, like this is a job for me. And then it interacts with the container runtime and tries to reconcile the differences. Kubernetes says this thing was deleted, but I'm still running it. Maybe I should shut down this container. Start up ones that don't exist yet. So why would you want to create your own? So for the kubelet, you probably don't, and you probably shouldn't. But we did anyway, as an experiment before KubeCon this past year, created something called the virtual kubelet. It's kind of an experiment. And essentially what it does is it interacts with the API server the same way that the normal kubelet does, and it reports itself to the API server as a node. So you actually look at Kubernetes, and Kubernetes sees a node that exists that doesn't really exist. There's no real node there. And basically what it does is any workload that gets assigned to it, it translates that, in this case I have Azure Container Instances, but HyperSH is supported, Fargate's supported now, and some others. And it basically translates it to these container platforms and runs them out in the cloud. So essentially it's a node with unlimited resources. So why would you even want to do that? Some examples would be batch jobs. You have a cluster large enough to run your normal workloads, but you want to run batch or CI/CD or things like that out in the cloud. Serverless. we keep thinking about like, how can I stop thinking about my hardware and nodes? And Kubernetes, is a great abstraction, but somewhere somebody had to do some capacity planning and decide how big of nodes do I need? How many of them do I need? So I think that things like virtual kubelet are definitely, and most of this stuff is all fairly early, and this is kind of the idea here is we should all be experimenting and trying new things. We're still figuring it out. But it would be really awesome to have the power of the abstraction of Kubernetes and not have to worry about the nodes themselves. CNI. So I don't know how many people are familiar with CNI. It's not mentioned a lot. But CNI is essentially the container network interface. This is what gets run every time you start up a pod to mount in the network interface into the container. So in the middle there, we have a CNI config file. This exists on every host. The important things here is third line down is the type, and then down we have the IPAM section. So CNI is kind of composed of two parts. One is the type itself, which actually creates the network interfaces, sets up routes, things like that, and mounts them in. And then we have the IPAM, which is the IP allocation module. So sometimes your network itself might want to manage the IP addresses that containers are getting, or might need to do additional things with the management of those. So why would you want to create your own? If you need multiple interfaces, and this happens, the cable example I used, they used one interface for pod-to-pod communication, and they needed a separate interface due to the way multicast works to be mounted in for all the egress of the video streaming. If you need to do custom routing for any reason, BGP, netconf, things of that nature, maybe you're doing software-defined networking, this is a good injection point for interacting with the network when containers come up and down. So kubeproxy. So kubeproxy exists on the workers itself. It's responsible for making services real. So if we look at a service definition and we have a cluster IP, that IP does not exist anywhere. It's basically just assigned out of a pool. Now kubeproxy itself will take that cluster IP and it will find all the matching endpoints for that service that are ready. And it will set up IP tables rules and things like that so that anything on the host tries to communicate with that IP, it will load balance between the existing endpoints. It will also bind to ports and things like that if you expose node ports. So much more. So we have things like extended resources. And these are, essentially you can set custom resource limits on your node. So maybe you're using an FPGA or something. You can set limits for some quantity that's available. And then in your pod definition, you can specify that it consumes this much, so you can hint to the scheduler. Init containers, these are containers that get ran before your pod actually starts up, so any of the normal containers. A nice thing about this is sometimes you need to do some initialization that might require keys or credentials that your actual application does not need to run. And these are great places to do that initialization step. That way the normal containers that are running, you're kind of eliminating that security threat there by not having to have the keys in those production containers. Initializers and finalizers, these are actually part of Kubernetes that I don't see used very often, but essentially we can set this up on the cluster for pods or things, objects that match specific criteria, where we can force things to be ran in the cluster. So essentially on startup of this pod, these initializers run and it can mutate the object and things like that. So we can force constraints, or we can do setup and teardown when we recognize containers of certain types coming up. I kind of mentioned a little bit readiness and liveness probes. Readiness probes are essentially telling services that this thing is healthy enough that it can be an endpoint in the load balancer. Liveness probes just means that Kubernetes shouldn't kick it. Node affinity and anti-affinity, this is so that we can attract workloads to specific nodes or repel them. You can use these a lot, like if you need things like GPU or things of that nature. Pod affinity and anti-affinity, this allows us to take containers and attract or repel them from each other. So let's say you're running Redis, right? We just have a normal leader-follower relationship between two components. We don't want them to run on the same node. And even then, you can set the boundaries here. So the boundary doesn't necessarily have to be a node. We can set labels for a rack or a particular data center or things like that so that we can ensure that they never exist in the same boundary layer. Istio, so Jeff was mentioning several things that Istio makes awesome and you get for free. If you install Istio into your cluster, which he talked about distributed tracing, and distributed tracing is glorious, but if you have a number of microservices and stuff running, trying to get everybody to spend the time to actually implement that is really painful. So the way Istio works is it injects itself on both the ingress and egress layers of every container. So you can enforce policies, but in addition, you can inject all the headers that you need for distributed tracing. So it knows at the very beginning of this process that this needs to have an ID generated for it, and then on the way out, it will add these things. So that's a quick way to get at least boundaries for how long each microservice took and things of that nature. And once you start seeing these things, it kind of helps you want to add more tracing inside the individual services. You can do things like request routing. You can do A/B testing so that you can send a certain percentage of your traffic towards specific pods. This works really great if you have like some production system and you need to run like maybe a canary or something like that to see whether a new version is going to work well. You can implement timeouts at that layer, retries. You can do kind of concurrent connections. You can limit them to upstream services. And this kind of helps with things like back pressure. Okay, so the next thing I want to talk about outside of how you can kind of inject yourself and customize Kubernetes to fit your needs is building abstractions on top of Kubernetes. So kind of at the beginning, I led with, Kubernetes isn't the thing, it's the thing that gets us to the thing. So we need to start talking about what it is that we want to interact with, because all these YAML files is not it, and it was never meant to be. So we've got stuff like Helm, right? So Helm is, if people haven't heard of it, it's like a package manager for Kubernetes. And this helps, right? When we think about managing an application as a whole, right? Like, let's just say a blog. We might actually have the persistent volume claim. We might have something for the database. We have the front end for it. We have config maps. We might have secrets for the database and for the credentials for the blog itself. Like now we're talking, 5, 6, 7 things that get managed, and it gets painful when you need to run multiple versions of these things. So Helm kind of allows you to templatize that and then fill in the values and treat everything as one application, deploy it as one, roll it all back as one. And I think this helps, but somebody has to create these YAML files. OpenFast, I don't know, how many people here are doing like functions as a service at all? Serverless? Okay, we've got a couple people. So I'm pretty new to serverless. I haven't drank the Kool-Aid yet, but I see some uses. But OpenFast essentially allows you to do functions as a service on top of Kubernetes. And I think this is where it starts getting more powerful. The PaaS is dead, but long live the PaaS, right? Like people are going to want platforms as a service. But now they can all communicate kind of at the same level to the operations folks who only have to worry about Kubernetes. Draft. Draft is another way of kind of making things easier. It essentially can do heuristics on your code base and figure out what programming language and framework that you're using, and then generate Docker files and Helm charts based on kind of known best practices for that particular language or framework. And I think this is a step in the right direction, right? Like we're no longer having to train all of our developers on creating Docker files and Kubernetes spec files and things like that. I think at some point, those things need to go away for the average developer. Pachyderm is really interesting. I should have put a screenshot of the UI here, but it's essentially a data pipelining system. You can use a UI to kind of configure the input and all of the steps in the chain, which ones require GPU, and it kind of manages creating all the pods and resources and making sure they end up on nodes with GPUs and that the data gets forwarded, and kind of tracks the data versioning and provenance. And the important thing here is to look at like all of these things that we're creating are all built on the same primitives underneath. Like Kubernetes can start becoming the assembly language of distributed systems for us. How many people have seen Metaparticle? Okay, we've got a couple. So Metaparticle is like this really, really ambitious project by Brendan Burns, who's one of the co-creators of Kubernetes. But I think this highlights the point really, really well that we need to democratize the creation of distributed systems. Like, everything is at scale now, and we've got more and more developers coming in, and they need to be able to create distributed systems without having to have, an insane background in it. So his idea is, essentially creating libraries within languages that you can include and kind of expose these distributed systems concepts. So I don't know how many people here are familiar with Go. I promise it won't hurt if you're not a Go person. But this is an example in Go. Essentially, you include this library. You tell the app to containerize itself. You say, I want 3 replicas. Here's kind of my Docker repository and things of that nature. And now when you compile this and you run this application, it will containerize itself. It will push itself up to this Docker repo, and then it will deploy itself in Kubernetes, running 3 replicas. And maybe this isn't the thing, right? But I think it's important that we start thinking about this. Like, what language do we want to speak to Kubernetes? Because now kind of the sky's the limit. The complexity of dealing with the infrastructure itself is kind of been taken away from us. So here's another example. Essentially what changed here is instead of saying 3 replicas, we said we wanted 3 shards, and then we gave it a regular expression for the URL to use as sharding. Now this will actually deploy a stateful set, and it'll set up all of the services and a sharding service that will get hit, and then you can kind of ensure that whatever the username is, they always end up hitting the same shard. And this is really powerful. So the future. So kind of as we stated, like, Kubernetes was never intended to be the top layer. And like, I love Kubernetes, and I've been, a big fan for years, but it's not an off-the-shelf product either. It's a starting point, and I'd love to see what people start coming up with for their own solutions, and eliminating the amount of time it takes to create entire distributed systems from scratch, when a lot of the components exist already. When we think about like the controller patterns and schedulers and things like that from Kubernetes, start customizing it. And the part that I'm really looking forward to is the things that we start building on top. And if you've got ideas, I would love to hear them. I think that we're in a perfect time to play and experiment. With that, thank you. I'm guessing she's going to ask for questions. Do we have time?
I think we have a minute or two.
Okay.
And you have just blown our minds with a million ideas of things that we can do and build. So I'm going to give people a possible opportunity if they want to ask you a question or two. Everyone is just going, there's so much to think about.
Would you recommend the operator pattern or like a Helm chart right now? Like, where do you think we're at with that?
Okay, wow, I guess this works now. So I think they solve 2 different purposes, right? So the operator pattern is really for kind of creating self-service infrastructure, where you're baking operational knowledge into something that's already running in the cluster, that is kind of aware of desired state of this thing, and kind of making that happen, and upgrade strategies and things like that. Helm charts are really for managing the number of YAML files that it takes. So you'd have one for your service, for your pod, maybe a couple pods exist. And they're basically just templates. And then that's your chart. And then you can just Helm install WordPress or something like that. And you can basically pass arguments saying this is the version of the container I want to run and things like that. So I think they solve two different problems.
I feel like I want to ask a question myself, so I will really quick, and then I'll give the mic to someone else. It seems like at the end there, you showed us a whole bunch of interesting projects. Where would you recommend people start if they want to dive in with customizing Kubernetes themselves?
So I think the important thing is I think as a community, we start collaborating on what the abstractions are and start talking about like what the end interface is that we want to consume. But one of the things that I'd love to start seeing people do is creating their own controllers and creating more operators for things that we all run, like Elasticsearch or Redis or whatever. Like these things are going to be powerful for the community, but also, step in there, and if you've got kind of unique constraints inside your infrastructure, like feel free to create a CNI plugin or your own scheduler and things like that.
With respect to Metaparticle, where do you feel the balance lies in terms of like the Helm charts, in terms of how they describe a topology versus what's kind of buried down at the specification within the Metaparticle implementation of a microservice?
So the question was kind of how do I differentiate like Metaparticle from like a Helm? Yeah, so I think Helm is an awesome project that helps with the management of the YAML files, but I also hope for the future that we're still not working at that level, right? That someday the ease of use of I know I'm running in a Kubernetes cluster and I need a distributed lock, and this is the name of my distributed lock, and I just include a library, and I just know that nobody else in the cluster can get that lock. I think we need that. I don't know whether Metaparticle is how we get there. I think it's a fantastic idea, an experiment, and a conversation starter on how we get there, because ultimately we need to democratize the creation of distributed systems.
I like that. We're hoping for a YAML-free future.
A YAML-free future. I like that.
Hey, just a quick question on the for hybrid environments, like on-prem, cloud, VMs, containers, are the options you listed? What would be the right fit?
So the difference between like you want to use VMs and containers kind of together?
Right, like the stateful stats, and you're running your.
So, I mean, containers are fantastic, but I think that there's a lot of problems that VMs solve too, right? For instance, a container is not a hard security boundary, right? Like we can do a lot of things to make containers more secure, but ultimately, if you're running an out-of-date library in your container and a vulnerable kernel, I can escape the container and I have access to your host, right? So if you have like really, really hard security boundaries, maybe containers, like say you're doing multi-tenancy, right? And you've got different departments or things like that. Like, you may still need VMs. There's some interesting cases though in cloud where, like for example, ACI, you get to run your pod, but you actually are in a VM there. There's things like virtual kubelet, where your provider could actually spin up a VM and run just your container inside that VM. I think people are still trying to figure out the hybrid approach, but I don't think VMs are completely going away.
Everything old is new again, and we're going to have to keep building on the systems that exist. Who knew? All right, give it up one more time for Erik St. Martin.